Scalars and vectors. Basically, we're going to look at the difference between what is a scalar and what is a vector, and the different things that we can do with each. Scalar, very simple. It's a measurement. It has a number. It has units, but it does not have direction. A vector has a number or numbers associated with it. It has units associated with it, but it also has direction. Okay? Vectors are quantities that say how much and in what direction, such as displacement. Okay? How far have you changed your position? Velocity, how fast are you going and in what direction? Acceleration. Okay? How much is your velocity changing and in what direction? Force, what direction are you pushing and how hard? Momentum, electric field, all of these are vectors. Scalars, things like mass, how much matter, time, okay, energy is a scalar. So once again, vectors are going to be quantities that not only do we have to give information about, how much, okay, and certainly there's going to be a unit associated with whatever dimensionality we're talking about, but again, we've got to represent in 2 dimensions which way are we going in the x and the y direction. In 3 dimensions, we might even have to add the extra z direction. So, vectors we typically represent with an arrow, like this little cute dachshund right here. The tail is basically wherever the vector is representing that point in space, or where a particular vector is being applied. That is the origin, what's being measured. And then the head to tail, this arrow, represents what direction the vector is pointing, but also what is the value of the vector. The longer the vector, typically the greater the representation that we have. So with vectors, again, arrows are a very nice way to represent them. And in terms of symbols, if we have a vector as a variable, the symbol is typically some letter with an arrow on top of it, or if the arrow is not available due to the typeset, will oftentimes also represent vectors with a bold form of the letter. So the vector A, again, has an arrow on top of it, or in this case, it's just represented as bold. Very simple example of a vector is a displacement vector. Displacement says how much is your position changed and in what direction. Here we have a campsite and we have a lake. We can reach that lake a number of different ways. Displacement doesn't care. Okay? It simply asks, what direction did you go? Okay? And how far did you go? Here's my position at the campsite. It's changed by this much to get to the lake, often roughly the northeast direction. Okay? So I represent that displacement, that movement from initial to final with this arrow right here. In terms of nomenclature here, how we might write out a vector, sometimes you might just see a vector by itself, like A with an arrow on top. Sometimes we use subscripts to define or describe what exactly is taking place. In this case, D, capital D, represents displacement. We know it's a vector because there's an arrow on top. And we know that it represents a displacement from A to B because we've used subscripts to show them. Okay? Now, a vector, again, is both direction and magnitude. How far, how much. I'm sorry, what direction and how much. The magnitude of the vector is the scalar form of the vector. It says, just ignore the direction for now. How much? In this case, we went 6 kilometers northeast, ignore the northeast, and we're just left with 6 kilometers. Just like we use absolute values to say, hey, ignore it if it's positive or negative, for the vector, the absolute value sign has a different meaning. It means just disregard what direction. Okay? Give me just the number value. And again, we have two vectors here from A to B. If we travel back from the lake to the campground, then our displacement would be vector dB to A. All right? Now, you will hear different terms that we will use throughout the course. One term that might come up is antiparallel. Antiparallel means the two vectors are pointing in opposite directions. Okay? DAB and DBA both have the same length. So we would say, well, their magnitude's the same. Okay? But each direction is 180 degrees different. Okay? We take this vector and we rotate it 180 degrees, we get the other vector. We would then say these two vectors are not just antiparallel, they're also opposites to one another. Just as though 3, okay, and -3 are opposite numbers, okay, here these two vectors are pointing in opposite directions. Mathematically, we can represent opposites like this. Again, their magnitudes are equivalent, but their directions are opposite. And again, the way we represent vectors is we try to oftentimes draw them to scale. So on this map, if 6 kilometers was the distance between the campsite and the lake, perhaps every 2 centimeters would be used to represent that. Let's talk about some other terms. We've already talked about antiparallel, going in different directions. Obviously, if antiparallel is 180 degrees apart, parallel must mean in the same direction. Okay? So if A and B are pointing in the same direction, we say they're parallel. They don't have to have the same magnitude. They just need to point in the same direction to be parallel. Antiparallel, 180 degrees apart, even though these two vectors have different magnitudes. Of course, the previous example had one vector antiparallel to the other, and the two vectors were equal and opposite, equal in magnitude. So A is antiparallel to -A in this case. Now, in some cases, we will have many vectors on a particular diagram. Okay? Vectors are equal to one another if the direction is the same and their magnitude is the same. It doesn't matter where their origin is. A and B both have different origins here, so they represent vectors at different points on my diagram. All right? But we say they are equal because the magnitude is the same and the direction is the same. Orthogonal. We'll also use this term from time to time. Usually we try to say, perpendicular. But if the two vectors, if the two directions are 90 degrees apart, then we use the term orthogonal, which has an even more general term in mathematics. It has to do with linear independence. Okay? But for our purposes, orthogonal, we're just like, okay, they're just perpendicular to one another. And again, here's some more explanation as to what each of these are. And again, some other examples. Here we have two parallel vectors. They're not the same magnitude. Here we have many parallel vectors, all pointing in the same direction, all at different magnitudes. Okay? Here we have parallel vectors and an antiparallel vector right there. And basically, with parallel and antiparallel vectors, as you add them or you subtract them, you only have to worry about the magnitudes. Okay? If everything's in the same direction, when you add them together, it's just the sum of the magnitudes. When you subtract them, obviously it's the difference. Okay, let's do a few different things right here. All right? Start with vector A. Vector A is pointing in the, if we set this up as a Cartesian coordinate system, here's our x-axis, here's our y-axis. A is pointing in the positive x direction using Cartesian coordinates. It is 1.5 log. Here we're using dimensionless units. We're not applying like a meter or anything like that to it. if A, okay, is such that B is equal to 2A, then B is twice the magnitude of A. A had a magnitude of 1.5, it was pointing in the positive x direction. Thus, the magnitude of B becomes twice as long. Notice we put a scalar in front of another vector. Perfectly fine. A scalar, as we'll see, alters the length of a vector. So in this case, this scalar helps relate the length of this vector to the length of this vector. All right? Because they're equal to one another, their directions are the same. In this case, C is negative 2A. Okay? That negative sign does something here. C is still twice as large as A is, as B was to A. But with that negative sign, it actually makes C anti-parallel to A. Here's a vector A, here's a vector B. What happens if we add them together? Well, A plus B, we have this much displacement, or we add this force to this force, whatever the vectors are. We say the resultant is the sum of each. If we're adding two vectors which are parallel, real easy. The length of A plus the length of B equals the length of the resultant. Okay? If we're taking two vectors and we're adding them and they're anti-parallel, well, we take the difference and that becomes the new magnitude. All right? So again, vectors, if two vectors are pointing the same direction, if they're the equal length, we say the two are equal. If the vectors are equal in magnitude but are 180 degrees apart in direction, we say the vector is the opposite or the negative of the other. We use the negative sign to represent this 180 degree difference in direction. What becomes difficult is when we try to add one vector to another vector, and they're not parallel and they're not anti-parallel. Okay? In this particular case, A goes off in this direction about 30 degrees above the x direction, and B looks like it drops almost 70 degrees in the negative direction off of the reference line in the x direction. So when I add these two, the length of A is not equal to the length of B. Okay? The magnitude of R is not going to be the magnitude of A plus B. You can clearly see that here. If I took A and I rotated here and then I put B with it, I would not get the total length of A. Okay? So, how do I handle this? Well, in taking two vectors, if I want to do the sum of the two, okay, and they're not, in the same direction like here, I can just add them. I need to do either, let me jump ahead a little bit. I need to either do a graphical addition of the two. Okay, this vector plus this vector, if I put them head to tail, I can get the R, and then I can measure that out and find the angle. Or I need to do an analytical addition of the two, where I break each vector down into a perpendicular component. Okay? Now, graphically adding vectors, really not all that difficult. You get a piece of graph paper, you plot out one vector, keep it to scale so you're on the graph paper. Add the other vector, doesn't even matter. The commutative property says A plus B is the same as B plus A. Doesn't matter which vector comes first. Putting the two vectors together, we're just doing head to tail in that particular case. If I'm adding more than two vectors, put the first vector, then add the second vector. The third vector just gets put on the end of where the last vector stopped. Then the other vector goes where that vector stopped. And the resultant of A plus B plus C plus D is just all the vectors stacked head to tail on top of one another, giving me my resultant. Okay? The other way we can do this is sort of a parallelogram method. We can take one vector here, A, one vector here, B. Okay? This creates the size of the parallelogram. Create a perpendicular line opposite to B where A ends, create a perpendicular line opposite to A where B ends, and the diagonal of the vector becomes the resultant. Okay, I can only do this with two vectors, but this polygon or other method works just as well. And as I said, it doesn't matter which vector you start with. Okay? The commutative property basically says order doesn't matter. And again, vector subtraction, A minus B is just taking A plus the negative of B. Okay? Here's A, here's B. A plus B would give me a resultant like this. But A, if B is going this way, we rotate 180 degrees. A minus B looks like this. Again, any scalar operation on a vector just operates on the magnitude alone. Doesn't affect the direction. If this is A, 3A is pointing in the same direction, it's just 3 times longer. Oh, it does affect the direction if it's a negative, then it turns it around. All right. Here's a graphical example. I take two vectors, here's A, okay, going north. A represents 20 kilometers going north, so on this each square represents 5 kilometers. I would plot this like this. I'm going to do the head-to-tail method. And then I go 35 kilometers in a direction 60 degrees, here's 60 degrees, west of north. So on my graph paper, this would be 35 divided by 5 is 7 centimeters long at a 60-degree angle. Okay? My resultant would go off in this way. So graphically, it's pretty straightforward adding these different vectors together. Again, it doesn't matter which vector I start with. Start at the origin right here. Okay? Where the first vector ends, the second vector begins, and you can add as many vectors as you want. Here's the parallelogram method doing the same thing. The result is pretty much the same. All right. Again, multiplying vectors by a scalar. All you're doing right here is changing the overall magnitude of the vector. So we look at the magnitude of B. If B is equal to alpha times A, the magnitude of B will be alpha times capital A. Okay? Notice that there's this absolute value sign right here, because the negative will just change the direction of B. Commutative property, this goes to, I'm sorry, I want to go to the associative property. Associative property, this just goes to the whole idea that which vector I choose to add first doesn't really matter. I can do A plus B plus C to come up with a resultant. I can do B plus C plus A. I can do C plus A plus B, C plus B plus A. The result is all the same. The associative property of addition basically, again, says we don't need to start with any particular vector. Unit vectors are a little bit tricky. Unit vectors was something that I really struggled with when I was first introduced to physics, and it's not something that we do a lot in this particular course. Unit vectors become more important in higher level physics courses, so we're not going to spend very much time on them. But like magnitude tells you how long a vector is, the unit vector of a vector tells you what direction it is without any magnitude. The magnitude is always normalized to 1. And we use this little hat symbol to indicate that this is a special type of vector. It's not just an arrow, regular generic vector. It is a unit vector, so it has been normalized to 1 using whatever units you are using. Unit vectors can be used to describe the direction. In this particular example that's in the book, we have a ladybug moving up and down a straw, and the positive unit vector goes this way, and the negative unit vector goes this way. It's a nice way of showing that if we just have all the directions that are parallel and anti-parallel, when we're adding things together, like putting 5 different displacements together, we can sort of ignore our normal rules of how we add vectors and use this unit vector to indicate if you're going down, it's positive, you're going up, it's negative, and just add the magnitudes to get the total result. Again, we won't spend too much time with unit vectors. I will introduce them from time to time because especially in higher level mechanics or in engineering classes, you need to be aware of this nomenclature. I never understood why they didn't use X, Y, and Z. But the symbol I goes to the X direction, the symbol J goes to the Y direction, the symbol K goes to the Z direction. So when you see I hat, that simply means it's a unit vector pointing in the X direction. J hat indicates a unit vector pointing in the Y direction. All right, just some more diagrams from the book. And again, reinforcing how you add and how you subtract vectors. Here's a practical example. Here we're dealing with 5 different displacements. Okay? You start in Tallahassee, Florida. You drive all the way to Jacksonville. That displacement can be represented by the vector A. Driving from Jacksonville to Daytona Beach is represented by the displacement vector B. Again, it doesn't matter which highway you take. It's just saying what was your initial position, what's your final position. Displacement's the difference between the two. From Daytona Beach, we go to Orlando. From Orlando, we go to Tampa. From Tampa, we go to Gainesville. Okay? So, from this, we can actually find the displacement between Tallahassee and Gainesville by putting together all the different vectors. Okay? Adding A to B to C to D to E, that is going to give us R right there. Again, this is a graphical way of doing it. Here's some more examples. You can look through them in the textbook to just get a handle of it all. And in fact, some of these you might try to also do analytically to see if your graphical results agree with the analytical results.